Good morning, everybody. Let's start our lecture. In the previous lecture, we have discussed about um, the basic problem, the fundamental problem of mechanics, and that is solving the equation of motion. We already have explained to you that the acceleration of a body, we are usually interested in the question, how would the body move if it is subjected by an external force? And after knowing the external force, we can know the acceleration. But the external force and the acceleration are usually given, not in terms directly in terms of the time variable. They are usually given in terms of the position and the velocity of an object. Like for example, when the body is tied to a spring, then the position of the body will determine the force acting on it because the force on the spring depends on the extension. And if the body is moving in air, then the velocity of the body will determine the air resistance acting on the body. The faster the body moves, the higher the air resistance. And so that result in a position and velocity dependent acceleration. And so we end up with the equation of motion, which involves the second derivative of the position with respect to time be equal to a known functions of acceleration as a function of position and space, position and velocity. But that is in general a difficult equation to solve. And we are interested and we can only let you know how to solve that equation for the simplest case only. And so in our previous lecture, we have discussed about how to solve the equation of motion for the simplest case of a uniform accelerated motion. And now we come to the more difficult examples. Okay, the so-called more difficult example is not that difficult. Here we only introduce to you how to solve a time-dependent acceleration, and for the simplest case of position and velocity dependence acceleration. Now, so let's talk about the first case, the time-dependent acceleration. Now, what we mean is that we are given a force acting on the object as a function of time. The function is given explicitly in terms of time, not the position and the velocity. Now, if you have a machine that can exert a certain force on an object, and you know precisely what the force is in a particular time, then you have a full description of the force as a function of time. That is what we mean, okay? And in that case, the force divided by the mass will then give you the acceleration by Newton's second law. And so you have the simplest equation of motion. That equation of motion is dv dt, which is the acceleration, be equal to a known function, a as a function of time. So you can see since the right-hand side is a known function in t, so you can integrate this equation to give the velocity. And so the velocity is now given as a function of time, okay? And the velocity is equal to dx dt by definition. And so you can integrate this equation further to give the position of the object as a function of time. So so it involves two integration in solving the equation of motion, and that is quite straightforward. Okay. Now I illustrate to you a very simple example. Suppose the acceleration is not constant, but is linearly increasing with time, and that is given by a constant beta multiplied by the time t. And initially, I assume the body starts from rest, so the velocity is 0, and the position is also 0 because it starts moving from the origin. And we are now required to find the velocity and the position as a function of time. Now, so the first equation of motion is simple. It only consists of the acceleration being equal to dv dt. And since our acceleration is beta t, we substituted the a into this position. Now you can have a very straightforward integration. I integrate both sides of the equation, I get the velocity. And integrating beta t will simply give me beta t squared over 2. And do not forget, we have an integration constant here, okay, because this is an indefinite integral. Now, we are now in place to, we are now ready to insert the initial condition. At time t equal to 0, the velocity is 0. And so when we put the t0 into this equation, we should have v equal to c equal to 0. And that means c is equal to 0. Okay, and so we would have the velocity given by half beta t squared. But this can be expressed in terms of the velocity can be expressed in terms of dx dt. So now we have another differential equation to be integrated. And integrating once more, we get the position as given by this expression. Okay, and integrating t squared will give me t cubed divided by 3. So together with these two, we have 1/6 beta t cubed, and we have another integration constant c prime. And given the initial position of the particle to be 0, when we substitute t to be 0 here, x is equal to 0, and so c prime is equal to 0. And so we have x equal to 1/6 beta t cubed. So that involves only two very straightforward integration. The only tricky point is that do not forget to insert the initial condition. Okay, you are given these two initial conditions to insert into the equation to give a full description of the motion. Now then we come to more difficult situations about a position and the velocity dependent acceleration. Now, in this case, the force acting on the object is given as a function of the position x and the velocity v. Now, the problem is how x and v depends on time, we don't know. Okay, before solving the differential equation, we don't know how x and v depend on time. But f is given as a function of x and v only, but not in terms of time. So that means the equation cannot be integrated in a very straightforward manner. Now we can get the acceleration by dividing the force by m, but that is still a function of x and v. And so we got this equation of motion. Now, if you take a deeper look at this equation of motion, you find that on the left-hand side, this is the dt, the acceleration. A is a long function, but that long function is given as a function of x, the position, and also the velocity. And the velocity is given as dx dt, right? So the right-hand side can be written as a function of function a, given as a function of x and dx dt. So that results in a complicated differential equation. Because we don't know the x dependent, how x depend on time before we solve it. So there is no way for us to integrate the right-hand side in a straightforward manner. That is the difficult problem. Now, so in this situation, solutions in a closed form is possible only for the simplest case. And for complicated situation, you have to do it numerically with using a computer. Okay, so that is the difficult part. Now, we are not going to introduce to you a complicated equation, but we simply will highlight several important cases in physics, and they are simple enough for you to solve in this course. And the first case we want to study is the motion of a body of an object in a viscous medium. First, we handle the case without gravity. Now, suppose you have a ball of mass m or a bullet, whatever you like. It has a mass m as is injected with an initial velocity v0 into a viscous medium. The viscous medium may be water or some kind of fluid you like. And so the medium exerts a force to resist the motion. Now we neglect gravity here for the sake of simplicity. Okay, we can imagine that this is happening in deep space where gravity is not present, or the phenomenon is happening so fast, the velocity is so large that the effect of gravity is not important. And so the viscous force is given by this empirical formula. It is proportional to the velocity. So the higher the velocity, the larger the resistive force. Okay. So imagine if you are flying fast in the medium, you will be exerted by a larger resistance. That is what the equation means. And it's we assume that for simplicity, the force is directly proportional to the velocity. And so the proportional constant between the force and the velocity is the constant K. Okay, K is a given constant. It depends on the properties of the medium and also the shape, maybe the shape and area of the ball. Okay. Now the negative sign here has a meaning. The negative sign means the velocity, the force, the resistive force is in opposite direction to the velocity. Because when the body goes this way, the resistive force tends to oppose it, right? So it must be in the opposite direction. And a way to specify it is to add a minus sign before the velocity. So the resistive force is always opposite to the velocity. Okay. Now we emphasize that this is only a simplest model. We assume the F and V are proportional to each other, and this is not quite correct for air. If you later we will study air resistance, and we will find that for a large object moving sufficiently fast in air, the drag force or the air resistance is not exactly proportional to V, but a better approximation would be V squared. Okay, so this is not quite correct for air, but suppose this is correct for some viscous medium like water and oil, something like that. If you have a ball projected into oil, that is the typical resistive force that the ball might experience. Now, so the Newton's second law will be like this: the force divided by the mass will give you the acceleration, and so it will become minus k over mv, and we write a shorthand. We introduce this constant b be equal to k over m. That is the definition. We only want to simplify the equation a bit. And so the equation of motion will be equal to, given by dv dt, equal to minus bv. That is the simplest first order differential equation. Now let's take a look at what this equation means. Because you are now trying to solve a differential equation, but not a algebraic equation. For algebraic equation, you expect to have a solution. For example, you solve a quadratic equation. You expect that the solution x is given as a number, right? Given by a formula, and that formula will eventually give you some number when you put in the constant, right? But for differential equation, you are not expected to find a number. You are required to find a function. You are required to find the function v as a function of t. Okay, so you are required to find that function in terms of the independent variable t. That is what you want. Okay, and what this equation says is the following: you are required to find a function, okay, function v as a function of t, such that when you differentiate it once, it will become itself. You give you back the function v, but the differentiation will introduce an additional constant minus b before the v. That is what this differential equation means. So you are going to find that function. Okay, after differentiating once, it goes back to itself, but you have an additional constant of minus b before the function. Okay. Now, what kind of function will obey this property? We can think of the exponential function, because the derivative of exponential function will go back to the exponential, right? This exponential function doesn't change by a differentiation. And if you put a constant in the time dependence, if the t dependence has a constant b that goes before it, then when you differentiate it, the constant will be pulled down by chain rule, and so you got the additional constant. So that means we can guess a solution to be in this form. Okay, we can guess the solution of V to be given by exponential to the power beta t, where beta is a constant, multiplied by another constant we call A. Okay, now we don't know what beta and A at this moment, but since we assume that this solution is going to work, we can substitute this solution into the equation to see if it really works. Okay, to check whether this solution really works for the equation. And we can also find what is beta and what is A after doing that. Now, so we just substitute V into this equation. And the left-hand side of the equation give you what? Give you the derivative of this, right? The derivative of the exponential function will give you back the exponential function. But by the chain rule, you differentiate beta t with respect to t, it will give you a factor of beta. Okay, so that is what is happening on the left-hand side. For the right-hand side, you simply have the V, which is this guy, multiplied by minus B. Okay. Now, so you see immediately if these two sides are to be equal, you after canceling the factor of the exponential factor, you get beta equal to minus B. So that means this equation can be satisfied for all time t if beta is set equal to minus B. That is what you mean, okay? When you do the differential, you do this derivation. Now, the fact that the exponential factor cancel on both sides, it means that the solution works because the equation can be satisfied for any time t. Okay, it does not depend on time anymore. So this can be satisfied for all time t as long as you set the beta, you set this unknown beta to be equal to minus B. That is what the derivation means. Okay. So we have the solution. The equation can be satisfied whenever beta equal to minus B. So we have this solution. But there is another problem. The A cancel on both sides, which means that the A cannot be determined by a direct substitution of the solution into the equation, right? So what determines A? Well, A is exactly determined by the initial condition. When the time t is set to 0, the initial velocity is V0. Okay, so when we put t equal to 0 here, the exponential factor is simply 1, and the initial velocity is equal to the V0. The V0 is a given velocity. So we now know our A is actually equal to V0. Okay, so that determines A. And when we put everything back to the solution, we got the solution of this equation is the solution of V is V0 exponential minus BT. Okay. Now let's look at the solution. Now I think you have learned this kind of solution. Maybe you have learned this kind of solution before. When you study the exponential decaying process of a radioactive nuclei, if you are given N0, the initial number of the radioactive nuclei to be N0, then the number of active nuclei will decay exponentially with time, right? And the exponential decay is given by this factor, e to the power in exponential, in radioactivity, you may have a factor of e to the power minus lambda t, right? And now you have similar thing for the velocity. You start with the initial velocity V0, you inject the ball into the medium, but the velocity of the ball decreases exponentially with time. So that is the decaying process. It's getting slower and slower because the ball is now being resisted by the viscosity of the medium. So the medium have decelerated the ball. Okay, so the ball velocity decreases exponentially with time. That is what the solution means, right? And it is physical because the medium always opposes the motion of the ball and tends to decelerate it. Okay. Now, the dimension bt in the exponential function is dimensionless. Okay, this is evidence when you look at the power series. I can explain to you like this, maybe. If you think about the Taylor series or the power series of the exponential function, what is this? Maybe I put it simpler. Instead of just instead of exponential to the minus bt, maybe I just write it as I can see. What is the Taylor series? I don't know if you remember it. It's something like this, right? If you learn pure mathematics, this infinite series is actually the definition of the exponential function, right? Now, but if you don't know about it, don't worry. I just want you to show you a few terms. Now, C cannot be dimension, cannot carry a dimension. Why? Because this series, you can see, C is added to 1, and C squared is added to C, and also 1. Okay? Now, when two things are of different dimension, they cannot be added up together. So the 1 does not carry the dimension. And so C must also be dimensionless. Otherwise, C cannot be added to 1, and C squared and so on, high order cannot be added to 1. And so C must be dimensionless. Now, that is true not only for the exponential function, for the sine and the cosine function, and also the other function, the other so-called elementary function, we also have its argument should be dimensionless. And so now we have the combination bt to be dimensionless. Okay, it does not carry a dimension. And that means if bt is dimensionless and t, the argument of a function is just the variable that it depends. For example, sorry. If I write a function as a function of C, then this C is my argument. Okay. Okay. So in this case, I have the function of C equal to e to the power C. Now, if bt is dimensionless, so if I find the dimension of it is equal to 1. So the dimension of B must be equal to the inverse of the dimension of time, right? Because it carries no dimension. This combination carries no dimension. And so the dimension of B must be of what? Must be time, the inverse power of time. Okay. So that means if we take the reciprocal of B, we call this 1 over B, tau. We define a variable tau, a constant tau, such that it is that by definition 1 over B it carries a dimension of time. We call this constant, we call this tau, the time constant, the damping time scale. Okay. Now, with this definition, and of course, you can also write B in terms of K over M. And so tau will become M over K. Tau carries the dimension of time. And in terms of tau, you can rewrite this equation. You can rewrite the solution of V as V naught exponential minus T over tau. Okay. That is how you rewrite it. Okay. Now, what does tau mean is the following. When the time t is equal to tau, okay, when time t is equal to tau, the factor in the argument in the exponent is equal to -1. So this factor becomes e to the power -1. And e to the power -1, if you use a calculator, you can find that this factor is about 37%. So that means at the time t equal to tau, the velocity has decayed to v0 exponential to the power -1. And this is about 37% of the initial value v0. So that means tau denoted the time scale for the motion to change substantially. And we define it as at a damping time scale. Okay. Now every motion has a certain time scale. The time scale is the time, a characteristic time that we define as such that the motion will change substantially. Okay, it is a time that we define to give you an idea of how fast the motion changes with time. Okay. Somebody asked me if it's okay to say tau is similar to the half-life. Tau is not the half-life. Because for the half-life, you have to decay for half of the decay of it's a time for v0 to decay to half of v0, right? But now you have a v0 decay to v0 to the power e to the -1. So that is different. It's not the half-life. Okay, but they have a similar idea. Okay. Now, so this is another angle which allows you to see that the constant tau actually has a dimension of time t. Now we start with the equation of motion. The equation of motion says the acceleration is equal to -bv, right? If you take dimension on both sides, you can see the dimension of acceleration is Lt minus 2, and the dimension of the velocity is Lt minus 1, right? So that means the direction of B is the dimension of A over the dimension of V. And when you divide this with this, you get T to the power -1. And so 1 over B, which is the reciprocal of this, has a dimension of time. And that is the dimension of the time constant tau that we defined previously. Okay. Now, in assuming the solution, we assume the solution of this form, right? In our initial derivation, we assume the solution to contain two constants, the constant A and the constant beta. But these two constants have different meanings actually in our derivation. The constant beta is determined by substituting the solution, the trial solution, into the equation. And we find that the equation can be satisfied for all time t, provided that beta is equal to -b. So that is determined by the parameter of the original equation. So once the equation is given, and when we substitute the trial solution, we can determine what beta is. So that is determined by the parameter of the original equation. But the other constant A has a different meanings. We find that A is equal to V0 by inserting the initial condition. So A is not determined by the parameter of the equation. It is determined by the initial velocity, with what velocity the object is now projected into the medium. So the two constants actually play a different role in our specification of the solution. Okay. The constant beta is there to satisfy the equation and is related to the parameter of the equation, while the constant A is specified by the initial condition, namely, in this case, the initial velocity V0. Now, when we describe a more difficult situation, that more difficult situation is we describe the vertical motion of the ball in a viscous medium in the presence of gravity. Okay. Suppose we have a ball and we project the ball vertically upwards. like what we did in high school. That is a vertical motion under gravity. But now we assume that is done not in air, not in vacuum, but it is done in a viscous medium. Okay, suppose we do it in water, or we do it in some viscous oil, and we project a ball vertically upward in a viscous inside the viscous oil. And so, what is the equation of motion? Now we first have to find the net force. When we project the ball upwards, we conventionally we tend to define we prefer to define the upward direction as positive. Now this is only a convention. You can also define the downward direction as positive. There's no problem for you to define it like this. But for convenience, we usually define the positive direction to be the direction of the initial velocity, just for convenience. Okay. If we define the upward direction to be positive, then the downward force of gravity would carry a negative sign. So the gravity force will be minus mg. This is only because of the convention. Since we define the upward direction to be positive, the downward gravity must carry a negative sign. This is only a matter of convention. If we define the direction to be positive, downward direction to be positive, the gravity will carry a positive sign. Okay, so it only depends on how we define the direction. It is only a convention. The minus sign before the gravity force is only a matter of convention. However, the minus sign that comes with the viscous force, the minus kV here, is not a convention. It has some physics. Okay, the physics is that the drag force or the resistive force acting on that body is in opposite direction to the velocity. So when the velocity is positive, is moving in a positive direction, the force is in a negative direction. If the body is moving in the negative direction, then the force is in the positive direction. It's always opposite to the velocity. So there is a physical meaning in the minus sign here. It's not arbitrary. It will not change by the change in convention. No matter we define the upward or downward direction as positive, we still have this minus sign that goes before the velocity. Okay. And so after dividing the force by the mass, we got the acceleration. We define K over M as B as before. And after dividing the whole expression with M, I got the acceleration as minus BV minus G. And so we have the equation of motion. This is equal to the acceleration dV dt. Now, you can see this is actually very similar to the differential equation that we have just discussed, except now we have additional constant G, okay, on the right-hand side, okay? So how to solve this equation? Well, we find that we can handle this constant by assuming that our solution also carried another constant, which I call gamma, okay? Now you have to substitute this equation into the equation to see if it's going to work. Okay, there's no guarantee for it to go to be working. You have to trial. You have to test your solution. Okay. Now let's substitute it. The left-hand side of the equation is dV dt, and so it gives you a beta exponential beta t as before. The differentiation of a constant is 0, so the gamma does not enter here. Okay, but for the right-hand side is minus BV minus G. So we have now, when V is given by these two terms, we have now three terms on the right-hand side. The first term is just minus BAE beta t as before. The second term is the factor minus B multiplied by gamma. This constitutes the second term. And also the last term is the constant minus G. Okay. Now we immediately realize that the blue part can be made equal to each other, just like what we did in our previous example. We can make them equal by setting beta equal to minus b. So by setting beta equal to minus b, the blue part will cancel each other. So that will be satisfied for all time t. The only thing that is left over is this two factor, minus b gamma minus g. But we can make them to be 0. If we choose gamma is equal to minus g over b, then these two terms added together will be 0. And the equation will be satisfied for all time t. Both sides will be equal for all time t if we choose these two conditions. Okay? So that's how we're going to work. We are going to choose beta equal to minus b and gamma equal to minus g over b. That guarantees the equations will satisfy for all time t. So our solution is going to work if we choose beta and gamma in this way. Okay. So this is our solution. But we still have an additional constant a to be determined. And just like what we did before, this additional constant a has to be determined by the initial condition. When at time zero, the velocity is equal to v0. So we substitute this into the equation. So the initial velocity v is equal to v0. v0 is equal to v0. And when we substitute time 0 into the right-hand side, we simply got a multiplied by exponential to the power 0 minus g over b. And the exponential to the power 0 is just 1. And so this is a minus g over b. And so we can solve for a. A is given by v0 plus g over b. Okay, that's a simple algebra. So now we have found a. So we substitute a back to this equation to find the solution. The solution is now given by v0 plus g over b. The brackets of it multiplied by exponential factor, exponential minus bt, minus another constant g over b. Okay. Now, apparently, we can see from this equation that the factor g over b, the term g over b, must have the same dimension as the velocity. Because the velocity, the initial velocity, is added to g over b. So g over b must carry the dimension of the velocity. Is that right? Otherwise, an apple cannot be added to an orange. If the two things are not of the equal dimension, they cannot be added together. So if the two things can be added together, then g over b must have a meaning of a velocity. Now, what is that velocity? We will determine it later, but we know that this is a kind of velocity. Okay, so we may define g over b by a velocity we call v infinity. Now, why we use this symbol? You know the infinity symbol is for infinitely long time or infinitely large amount of space. That's meant by infinity. Why we use this symbol? We will explain it later. But we define now the g over b factor as a velocity called v infinity. And as before, we define the constant 1 over b as the time decay time constant tau. Okay. And so with this definition, we write the solution nicely. The bracket is written as the term inside, two terms inside bracket is written as v0 plus v infinity. The exponential factor now becomes e to the power minus t over tau. The last term is also v infinity. So we have this equation. Okay. Now, having write the equation in this nice manner, we can now look at its meaning. But this equation looks a little bit complicated. Okay. So we prefer to look at the simplest situation. The simplest situation corresponds to the case of releasing the ball from rest. Okay, if I release the ball from rest, that means the initial velocity of the ball is 0. Okay, because V naught is the initial velocity. So by putting V naught equal to 0 into the solution, we are handling the case in which the ball is released from rest. We just release the ball inside a viscous medium and let it fall. Okay. Now, so if you put V naught equal to 0, we can extract a factor of V infinity O. We also extract the minus sign O, and so the two terms in the bracket become 1 minus e to the power minus t over tau. Now, what will happen? Initially, the velocity is 0. You can see. Initially, when I put t equal to 0, this is 1. 1 minus 1 is 0. So we have 0 initial velocity. And then the velocity increase with time because this factor, this exponential factor will decrease with time. So the velocity increase. Is that right? But in a negative direction, meaning that the velocity increased in a downward direction because the object is now falling. Is that right? So that's correct. The velocity initially is 0 and then it increased with time because this is accelerated by gravity downwards, right? But eventually, after a long time, and what we call a long time is actually we mean the time t to be much larger than tau, the time scale of the problem. In this problem, when the time t we choose to see is much larger than the typical time scale tau of the problem, then the exponential factor will go to 0. It will be almost 0. And in that case, we can neglect the exponential factor relative to this one. And what we get is that when t much greater than tau, the velocity is almost a constant. And that constant is equal to negative of V infinity. And so we can identify the V infinity as a terminal speed. It is exactly the terminal speed you learn in high school. When you drop an object in a viscous medium, like for example, you have a skydiver released in air, and the skydiver will be accelerated by the downward force of gravity. But eventually, the air resistance will be sufficiently high to just overcome the weight of the body. And when the air resistance becoming equal to the weight of the body, the two forces cancel each other. And so the net force acting on the person is 0, and the person falls with a constant terminal speed or the terminal velocity. That is what you learn in high school. This is exactly the terminal speed you learn in high school. Now the terminal speed in this case is given by g over b. If you like, you can rewrite the b in terms of k over m, and that becomes mg over k. Now, that is why we want to define the tau, because we want to know how fast the system change. If we are given some the information about the system, we have given the k and the m for the system, we can calculate the timescale tau. And from the timescale tau, we know how fast the system change. Okay, now this equation may be describing a lot of problem. You can describe, for example, a bullet hitting, striking into water. And a time scale will be very fast. It may be that all the things may happen in 1,000 of a second. So you need to know the time scale. So if you use the viscosity of water and if you use the size of the bullet to calculate k and m, you get the time scale of this problem to be 1,000 of a second, which means that it's happening really fast. But if you are dropping a small ball inside water, for example, all that thing happen to be very slow. It may take several tenths of a second for the ball to reach the terminal speed. And so you get another time scale. And so that's why we want to define this time scale, because we want to know how fast the speed is changing for the particular problem. Okay. And you can see the velocity, the terminal speed, can also be expressed in terms of this time scale. It's actually g tau. The acceleration multiplied by tau will give you the terminal speed. Okay. Now that is exactly what will happen. Now we don't discuss the case of a skydiver because we are not talking about air. For air, the air resistance will be more complicated. It may depend on V squared instead of V. So we talk about a simplest case of a ball falling inside a viscous medium. Okay, so when the ball is first released, it is accelerated by the downward force of gravity. But over time, the velocity increases. And so the viscous force acting on the ball also increases with time, because the viscous force is proportional to the velocity. And eventually, after falling a long time or after falling a long distance, the viscous force just balances the force of gravity. And the acceleration of the ball will become zero because the force is balanced. And you can see if the velocity become constant, if the acceleration becomes zero, then we can solve this equation for the velocity. And you can see the velocity is exactly the terminal speed, and is given by minus g over b. Okay, so this in v infinity, it can actually be solved by putting dv dt equal to 0 in the equation of motion. Okay, you only have to put dv dt equal to 0 in order to solve the velocity, and the velocity is exactly the terminal speed. Okay, so this solution means a ball is released from rest in the air is gradually accelerate downwards until the force of gravity is exactly balanced by the viscous force. And at that time, the ball falls with a constant terminal velocity. Okay. Now, we better have a break here. Okay, so you can have some time to digest what we have learned. So I stop the recording now.